Hello, today we're going to be looking at the solubility product constant, or KSP. You remember the K equilibrium? It's pretty much the same idea. So the first thing you need to do is recall that equation that we got for K equilibrium, where you had the products raised to their coefficients divided by the reactants raised to their coefficients. Since saturated solutions are equilibrium systems, if you remember we talked about how if you oversaturate with sodium chloride, the crystals will interchange between the solid and the aqueous state. We can apply this mathematical relationship to solutions. We will refer to our K equilibrium constant as KSP, where the SP stands for solubility product. So an example. For our silver sulfate saturated solution, so the silver sulfate will turn into silver and the sulfate ion. We can write our solubility product constant expression as this. So we have our KSP equals the concentration of the silver ion. And because there's this 2 up front here, we have to square that. We're multiplying that by the concentration of our sulfate ion. We're dividing that by the concentration of our silver sulfate. Okay, but remember from our early introduction into equilibrium constants expressions that the concentration of solids and liquids are not included in the expression because their amounts will change during a reaction and their concentrations will remain constant. Unless otherwise indicated, our examples will always involve dissolving solids to produce aqueous ions. Therefore, we will write our solubility product constant expression for a saturated silver sulfate solution as the same thing, just without the denominator. Okay, so we got rid of the denominator. All right, remember it's always very important to include those ion charges, so the pluses and minuses, in your equation. All right, here's an example. Write an expression for the solubility product constant, the KSP, for Ca3PO42. So first we have to begin by writing the balanced equation for the reaction. Remember, polyatomic ions remain together as a unit, so they do not break apart into separate ions. So we start with the Ca3PO42. And this is breaking into ions in an equilibrium state. So we're left with the Ca, and that's a 2 plus PO4 3 minus. I think my notes are a little unclear right now, but I think that's right. Now we have to balance. So if you notice over here, there's 3 calcium. So we have to balance with 3 calcium. There's 2 of the phosphate. So we balance with the 2 in front. Then we're going to write our KSP expression. So remember, KSP is the concentration of the products raised to the exponents times each other. We have to remember to write in our little ions divided by the concentration of the reactants. Okay, but this Ca3PO4 is a solid, so it's not included in our KSP expression. Solubility product tables. If the KSP is very large, the concentration of the product must be greater than the concentration of the reactants. This reaction essentially goes to completion, which all or most of the reactants are being used up from the products. If the EQ is very small, the concentration of the reactants is much greater than the concentration of the products. The reaction does not occur to a great extent. Most of the reactants remain unchanged, and there are few products to be produced. When KEQ is very large or very small, is not very large or very small, then roughly equal amounts of reactants and products are present in the equilibrium. So what does the KSP tell us? KSP, which is again just a special case of the K equilibrium, provides us with the same useful information. A lower value of KSP indicates the substance has a low solubility. It is generally insoluble. For ionic compounds, this means that there are very few ions in solution. So for example, the iron 2 sulfide, the FeS, is an example of a low KSP with a KSP of 4 times 10 to the negative 19. In a saturated solution of FeS, there would be few Fe2 plus and S2 minus ions. A very large value of KSP indicates the soluble substance. For ionic compounds, it tells us that there are many ions in solution. An example of a relatively large KSP would be for lead 2 chloride, or PbCl2, which has a KSP of 1.8 times 10 to the 4. A saturated solution of PbCl would have a relatively high concentration of Pb2 plus and Cl minus ions. So calculating KSP when concentration of the saturated solution is known. The concentration of a saturated solution of BaSO4 is 3.9 times 10 to the negative 5 molar. Calculate the KSP of barium sulfate of 25 degrees Celsius. So we're always going to begin our problems by writing out a balanced equation. So we start by what they give us. So the BaSO4, okay, and that is going to be in an equilibrium reaction with its ions. If you don't know what the ions are, you can refer to your periodic table of ions, which I would have given you in your duotang, just to see what their ionic charges are. Okay, next we're going to write a KSP expression. I didn't leave myself enough room, so I'm just going to write it over here. So KSP is concentration of the reactants. Oh, everything's balanced. I didn't have to add any coefficients, so it's just the concentration of reactants times themselves divided by the concentration, the concentration of the products divided by the concentration of the reactants. But remember that reactant is solid, so we don't have to include it. So the question provides us with the concentration of the BaSO4. Since we need to find the concentration of the individual ions for our equation. So we're going to we need to think logically. So we have 1 mole of each of these. So if 1 mole is being broken down, it's going to be broken down, and all the concentrations are going to be approximately the same. So that means the concentration of the BaSO4 is 3.9 times 10 to the negative 5 molar. Concentration of the Ba2 plus is the same thing as the concentration of the SO4, 2 minus, which is 3.9 times 10 to the 5. Okay, so we sub those values in to our KSP expression. And that's going to be multiplied again by 3.9 times 10 negative 5. So our KSP ends up being equal to 1.52 times 10 to the negative 9. Okay, so calculating iron concentration when KSP is known. The KSP for MgCO3 at 25 degrees Celsius is 2.0 times 10 to the negative 8. What are the ion concentrations in a saturated solution at this temperature? Again, always, always, always start with your balanced equation. Okay, so you start with what they give you. Okay, and it breaks down into its ions. Okay, then we write our KSP expression. Okay, I'm not going to include the MgCO3 in the denominator because we know it's a solid, so we know that it's just not going to be there anymore. So for this example, we're given the value of KSP and need to find ion concentrations. We let our unknown ion concentration equal X. The balanced equation tells us that both Mg 2 plus and CO3 2 minus have the same concentration, which means that we can say the concentration of Mg equals the concentration of CO3, which equals X. Okay, that means in my KSP expression, I'm going to say this is X times X, which I know becomes X squared, okay, which is equal to the number that we're given. Okay, so to find what just X is, we have to square root it. So we end up with X equal to 1.4 times 10 to the negative 4. Okay, and that X is going to then be the concentration of your magnesium and the concentration of your CO3. All right, another example as we're calculating ion concentration when the KSP is known. So we have silver chromate has a KSP of 1.1 times 10 to the negative 12. We're going to calculate the molar concentration of the silver chromate in a saturated solution. Always begin with this balanced equation. So we start with what we're given. Break down into our ions. Okay, there's this 2 back here. We need to put it up here so that we have the same number of silver atoms on the products and the reactant side. Okay, that means that our KSP is going to be the concentration of Ag squared. Don't forget your ions. Sorry, it's a little messy. Okay. Now, for this question, you're given the KSP, but need to find the concentration of the AgCrO4 solution, not the concentration of the individual ions. But in order to solve our KSP, we first must find the ion concentration. The balancing coefficients from our equation tell us that the concentration of the silver ions will be twice as great as the concentration of the chromate ions. Okay, so we can tell that because there's this 2, so there's going to be twice as many silver ions as there are chromate ions in equilibrium. The concentration of the silver chromate solution will be equal to the concentration of the chromate ions. So I'm just going to do my work on this page so I have some more room. So we're going to let X be the concentration of the CrO4 2 minus, which means then that the concentration of the silver is 2x. Okay, we had our KSP from before. Okay, then I'm going to sub in my values. So the concentration of Ag plus is 2x, and that's squared. Concentration of the chromate is just x, and that is equal to, because we're given the KSP, 1.1 times 10 to the negative 12. Okay, now I have a little bit of math to do. 2x squared is like 2x times 2x times x. So when I'm multiplying like this, what I can do okay, so I'm going to multiply all my numbers, so I end up with 4, because everything's multiplied together. Then there's 1, 2, 3 x's multiplied together, so that's x to the power of 3. That still equals the same KSP. Okay, then I have to do some algebra, so I divide by 4 because I'm trying to get x by itself. So I end up with x cubed equals 2.75 times 10 to the negative 13. Okay, then I have to take the cube root, because it's cubed, on both sides. So finally, I'm left with x is equal to 6.5 times 10 to the negative 5. Okay, so that is the concentration of the chromium, or chromate. It's also the concentration of the silver chromate. And if I multiplied it by 2, it would be the concentration of the silver ions. This last slide. The common ion effect is another example of Le Chatelier's principle. The common ion effect tells us that the solution of an ionic compound is decreased, the solubility of an ionic compound is decreased by the addition to the solution of another ionic compound that contains one of the ions involved in the solution equilibrium. If we have a barium sulfate solution, the solid salt in equilibrium with its ions. So the barium sulfate is in an equilibrium system with its ions Ba2+ and SO4 2-. If we then add solid barium chloride to this solution, which dissolves to produce barium and chlorine ions, we are increasing the concentration of the barium ions in our solution. The new Cl ions will remain in solution as spectator ions. The barium ions is the common ion to both sides. The Chatelier's principle tells us that if the concentration of one of the reactant participants is increased, then the equilibrium will shift to use up the additional substance. So, adding more barium will force the equilibrium to shift to the left, the reverse direction, in order to use up the barium ions, producing more solid barium sulfate. The concentration of SO4 will decrease, indicating that the solubility has decreased. Alright, so that's today's lesson. We'll see you tomorrow in class to do some assignment questions.